Alright, so in this video, I'm gonna be talking about another approach for contrastive networks and this important paper in 2023, which is called Hierarchical Exemplar Contrastive Learning for Unsupervised Relation Extraction. Unsupervised relation extraction aims to extract the relationship between entities from natural language sentences without prior information on relational scope or distribution. Existing works either utilize self-supervised schemes to refine rational feature signals by iteratively leveraging adaptive clustering and classification that provoke gradual drift problems, or adopt instance-wise contrastive learning which unreasonably pushes apart those sentence pairs that are semantically similar. Simon adopted skewness and dispersion losses to enforce relation classifier to be confident in the relational feature prediction and ensure all relation types can be predicted averagely in a mini-batch. But it is still requires exact number of relation types in advance. To overcome these defects, this paper proposes a novel contrastive learning framework named HiURE, which has the capability to derive hierarchical signals from a relational feature space using cross-hierarchy attention, and effectively optimize relation representation of sentences under exemplar-wise contrastive learning. So this task of relation extraction in NLP aims to discover the semantic relation that holds between two entities from plain text. For instance, this is head and this is the tail. So we can extract a relation people and then person, place of birth between two head, tail. So it's hierarchical. And head, tail entities. And the extracted relations could be used in various downstream applications, such as question answering. But unsupervised learning is promising. Lots of effort. For example, in the first article about contrastive learning was that an image was augmented, so it was purely self-supervised. But then people use supervised contrastive learning as well. So when we talk about contrastive learning, you can use it both supervised and self-supervised, or even a combination of them. So lots of efforts are devoted to alleviating the impact of human annotations in relation extraction. Unsupervised relation extraction is especially promising since it does not require any prior information on the relation scope and distribution. The main challenge is how to cluster semantic information of sentences in the relational feature space. So this is just an example of hierarchical structure. So what is a gradual drift problem? Therefore, our intuitive approach is to alleviate the dilemma of similar sentences being pushed apart in contrastive learning by leveraging the hierarchical cluster semantic structure of sentences. Nevertheless, traditional hierarchical clustering methods all suffer from the gradual drift problem. Thereby, we try to exploit a new approach of hierarchical clustering by combining propagation clustering, so combining clustering and attention mechanism. We first define exemplar as a representative instance for a group of semantically similar sentences in certain clustering results. Of course, different papers use different words. This paper uses exemplars, another paper uses prototypes, So there are different things. Some people use centers, they call it centers. So exemplars can be in different granularities and organized in a hierarchical structure. And this is the architecture. First we give it to a deep transformer, in this case BERT, and then we have a contextual relation encoder, because we know the head and tail, and we can represent that for the task of relation extraction much better. And then we give it to this propulsion encoder, and of course here we are also doing the clustering part, which is just the hierarchical cluster results. So sentence representation will be augmented through random spans with fixed entities. Because in NLP is difficult to do. We have very limited ways to do augmentation. In contrast to computer vision, they have rotation, translation. There are many ways to create different views of a single image. But here, for example, they use random spans in NLP with fixed entities. And then this HPC that I said takes momentum features H as input. So this is just the input to this algorithm, and generates L layers of clustering results together with L exemplar sets. So takes H and H prime for instance-wise, while H and C for exemplar-wise contrastive learning. So the contributions, there are three major. First, we develop a novel hierarchical exemplar contrastive learning framework that incorporates top-down hierarchical propagation. Then we demonstrate how to leverage the semantic structure of sentences to extract hierarchical relation exemplars, which could be used to refine contextualized entity-level relational feature. Then we conduct extensive experiments on two datasets, achieve better performance than existing state-of-the-art. So they proposed, which consists of two modules. First, the contextualized relation encoder, and then the hierarchical exemplar contrastive learning. As illustrated in that figure that I showed you, the encoder module takes natural language sentences as input, where named entities are recognized and marked in advance, then employs a pre-trained BERT to output two contextualized entity-level features. Feature set H and H prime for each sentence based on random span. So this is the equivalent of their augmentation that they do in computer vision, but here we do it differently by just using random spans. The learning module takes these features as input and aims to retrieve exemplars that represent a group of semantically similar sentences in different granularities. So we leverage these exemplars to iteratively update relational features of sentences in a hierarchy and construct an exemplar-wise contrastive learning encode, which is called hierarchical extreme NCE. And then we use contextualized relation encoder for a sentence with T words, with each WI represents a word and two entities. Head and tail are mentioned. We follow the labeling schema, and we augment X with 4 reserved tokens to mark the beginning and end of each token. So we introduce these tokens to represent start, and these are end. Start or end position of head or tail entities respectively. So this X prime will be input token sequence for encoder, and span subscript indicates the random span words, because different augmentation, different span words. So considering relational features between entity pairs are randomly embraced in context, we use pre-trained BERT, or we could use pre-trained BioBERT in the context of biomedical text, or PubMed BERT, or there are lots of pre-trained models. You can just take it and do your fine-tuning for your any task you have. For example, you could, for the task of relation extraction, task of entity linking, task of name entity recognition, task of normalization, task of many different tasks in NLP. So whether we utilize the output B sub I corresponding to these tokens as the contextualized entity level features instead of using sentence level marker to get the embedding for a target entity, because it's more informative. This is important for contrastive learning purpose. We randomly select P words as random span from all context words in the whole sentence except for those entity words and special tokens to augment the entity level features as B sub span, where multiple different random span selections lead to different semantically invariant embedding of the same sentence. Then for every selection, we just concatenate the embeddings of the, of course, when I hear the word concatenate, I feel bad because we are creating cursive dimensionality. But in any case, the embedding of the two entity and P random span words together to derive a fixed length relational feature. So this H is the output of the contextualized relation encoder, which can be denoted as F theta. The random span strategy can get sentence-level enhanced relational features to construct positive samples directly and effectively, and its simplicity highlights the role of subsequent modules. In order to adaptively generate more positive samples other than sentences themselves to introduce more similarity information, we design hierarchical propagation clustering. So this is the algorithm that we use. First, we initialize S sub j. Then for L, because we have L different levels, we update according to that equation that I showed you. And then we have another loop inside this. We have another loop because we have exemplar set. Then if changes of E sub L have converged, then go out of this inner loop. So it comes to this outer loop. And it continues to set diagonal to preference and so on. So this is the overview of cross-hierarchy attention. The first part shows original data. The second part divides data points into two clusters and utilizes attention to update every point which contributes to the next level of clustering. So it's computationally expensive. And in practice, propagation clustering exchanges real value messages between points until high quality set of exemplars are. So it's like expectation maximization. And in another paper, I've explained the same kind of paradigm. It's very similar to that. And so A sub Aij to represent the suitability for I to choose J as its exemplar, for example, this one. So it's just a distance between point I and J. Responsibility Rij indicate the appropriateness for J to serve as the exemplar for I, and availability to represent the suitability for I to choose J. And then here we have the contrastive, that attention that we were talking about. Because we can derive CHA at layer L, but element JK is obtained by, it's just a scale softmax. And then the attention weights, these alpha, jk reflects the proximity between the exemplar j and exemplar k in layer L and measures the influence and interactions to corresponding data points between these exemplars. Typically, exemplars are visually close to each other, would have higher attention weights. Then we derive attended point representations at layer L+1 by taking the attention weight sum of its corresponding exemplar from the other exemplars. So finally, it's just a linear combination of these exemplars. And then we combine the attended representation with original one to obtain a better embedding, this embedding. So this hyperparameter lambda, this is just, lambda is not a hyperparameter, but a weighting variable to be automatically trained. Of course, they train it, but the important thing is that traditional instance-wise contrastive layering treats two features as negative pair, as long as there are different instances, regardless of their semantic similarity. So it updates encoder by optimizing the info and CE. So HI and HI prime are positive samples, while J prime here includes one positive and J minus one negative samples. Compared with traditional instance-wise contrastive learning, which unreasonably pushes apart many negative pairs and possess similar semantics, we employ inherent hierarchical structure in relations. So we leverage HPC on the momentum features, which contains L layers of cluster results with C sub L exemplars respectively. And so we define that contrastive layering just like extreme NCE. We call it extreme NCE loss. And E here is the corresponding exemplar of instance I at layer L. So it reminds me protonet in few-shot learning as well, because exemplar reminds me prototype. And finally, you can enhance this info and CE lace. We augment it with this extreme NCE loss that I explained here to have the total loss. So we have the total loss, but of course, because we also, I think here they draw inspiration from that moving average of BYOL method or moving average of Simsiam method. That's why they are also considering this to reduce that high frequency variations, because it's like a noise, too much variation. Your model varies too much. But if you use this one, it's a good idea. So this is the relation and hierarchy that they are derived from feature space and this data set. You see, at level 1, we have people, person, place, lived. And then 2 is like business, company, industry. Then you go deeper.